Hello, everyone. Jimmy Strand here from IU5. You're doing it. You're really doing it. You're sending a weather balloon into space. I am so excited for you. Not only will you get some fantastic high-res pictures and video recordings, but you will also be able to answer that age-old question of whether or not the Earth is round or flat. Okay, math people, I can hear you whispering about me. Round isn't exactly the perfect mathematical term to describe what we were um, talking about, but you certainly get the idea, right? Anyway, we're launching the balloon, and when doing this, we should have several questions. I mean, there are a lot of variables, right? Tons of questions, in truth. And hopefully one of them should be, how much helium should we put in the balloon before we release that mighty orb into space? And I guess wave at it slowly as it disappears into the sky. You can do that if you want. You don't have to. I always do. I think it's nice. Well, through the power of the internet and a completely free web tool, we can answer that question. So you see it before you on the screen. We're using something called the Perfect Performance Balloon Calculator. I thought with a title like that, there should probably be some echoes. So you, me, and whoever else is responsible for this feat in slow motion aeronautics will really need to use this tool, understand it, and with it, we will be able to determine the amount of helium that we need to put into our space balloon to do a lot of things, really. And by a lot of things, look at all the variables. We have balloon size, payload weight, positive lift, required helium, estimated burst altitude, average ascent rate, ascent time, all types of things. So, even though there are a ton of variables, notice there's an input and an output. So we're going to put in particular variables here, balloon, payload weight, positive lift. We're going to press this calculate button, and the output will be the required helium in our balloon, where this handy dandy calculator is estimating the altitude in which this balloon is going to burst, the average ascent rate, so how fast you're going to have to move your neck back to look at the balloon as it goes into space, and finally the ascent time in minutes. Those last two, ascent rate, average ascent time, those are more important for predicting where this thing's going to land. But we're focused on the required helium in cubic feet that we need to put in this thing. So at this point, I'm going to enter some variables. You can follow along if you want, but I'm actually going to do that in another video just in case I mess up. So we'll see you in a second. Bye. Hello, we're back looking at the balloon performance calculator, and this is the device that will ultimately tell us how much required helium we must put in our space balloon to get it to where we want it to burst in space. So looking at the input variables, we have the balloon size, the payload weight, payload mass, and positive lift. Two of these are fixed. The balloon size we're working with is a 350-gram balloon, and the payload weight, by the time you put in the Arduino and the GoPro and the container itself, it turns out to be right around 1,000 grams. So this is an important value. When you're completing your final prototype, ready to launch, that payload must stick around 1,000 grams to ensure that our calculations are correct. So the one thing we can modify is the positive lift. Now, changing the positive lift will change the required helium, the burst altitude, along with the ascent time and ascent rate. After some Google searching, it turns out that planes or jets travel around 32,000 feet, and if you go just a bit higher to around 40,000 feet, you can see the curvature of the Earth. So I got my handy dandy TI-83 simulator here, 40,000 feet, and we have to multiply by a little unit comparison here, 3048, and that's meters per foot, about 12,192 meters. Okay, great. So from there, you could say, hey, I just want to see the curvature of the Earth. If I get my balloon up to about 12,000 meters, it's going to pop, it's going to come back to the Earth. Great. So we need to determine a positive lift that will give us that estimated burst altitude. Through the magic of television, I've already figured out what that number is. It's around, I don't know, 9,000 grams positive lift. Okay, not exactly. It's a little bit higher, right? Looking at 12,500. Notice a few things here. The ascent rate, about 10 meters per second. That's pretty fast. 30 feet per second, general equivalent. And also the ascent time. It'll get to this burst altitude in about 20 minutes and begin to come back down. But what you notice is the amount of helium required is immense. 372 cubic feet. In the tank that you're getting, that torpedo tank, that only holds about maybe 240 cubic feet. So it's a tank and a half. Helium's expensive, so to only get maybe one launch per tank, you have to think about cost there. So what I like to do is, based on our experience from launching balloons in the past, we don't go after a burst altitude. We want to get the most unique pictures to get that balloon up as high as humanly possible. So what we really focus on is an average ascent rate. And we get that value to be approximately 1,000 feet per minute, which works out to be approximately 5 800 meters per second. So I'm going to modify my positive lift to get a value of 5.08 meters per second. Just take off some large values here from 9,000 to 8,000. Didn't change it too much. How about to 5,000? So we're at about 9 meters per second. Still not a ton. What about 2,000 grams positive lift? Closer. Let's get crazy. Let's go 700. Oh, we went below it, so we got to add, let's say 800. And I don't know, let's try like 860 or something. Oh, too much. 850. Still too much. I bet this is really fun for you to watch, as me trying to figure this out. So close. 830. Yay. Okay. So I'm going to write this number down. This is important to us. 830 grams positive lift. And the other valuable number here is how much helium we're going to need to get that ascent rate what we want it to be. So the burst altitude, that's around 73,000 feet. So that's pretty high, pretty dramatic. You're going to really see probably space and a good picture of the Earth, a large portion of it as well. And the other value we need is that 78 3/37 cubic feet of helium that we need to put into our balloon. All right, so the next thing I'm going to show you the volume calculations on, with a volume this large of helium in a balloon, what is the radius of that balloon, and more importantly, the circumference, right? Because we have to do some sort of measurement to make sure, because we don't have gauges on our tank to determine that we put this much helium into the balloon. I'm coming back with that right now. Hello and welcome. Are we still launching a space balloon? We are. And we're launching at a particular, let's call it velocity, about 5.08 meters per second. And you might have a few questions, one of them being, why does he write with a straight edge? It helps with the letter formation. Plus, it's a nice drawing tool as we're going through this. Remember, we had 1,000 grams for our payload, and this is a 350 gram balloon. Very cool. And certainly we could have said, oh, when this thing gets to, I don't know, around 40,000 feet, right, we want it to pop and then drift back with a parachute back to the Earth so that our friends on the ground can ping it, find it, and you can look at the video as moving forward of the cool things that you saw. Ultimately, is the Earth flat or round? But to do this, we use that balloon performance calculator, and we need to determine with a physical measurement how big this balloon's going to be. And we can do all of those things. So remember, using that balloon performance indicator, we received a volume of our balloon to be around, I don't know, 78 approximately and 3/700 cubic feet of helium. So that's the helium that when we fill this thing up, the volume of this balloon is around this number here. Okay, great. But how do you determine I don't know, a few things. What the radius of this balloon is, if we had to complete a physical measurement, or what's the circumference of this balloon. So if you were to take a string around the outside, what would the distance around this sphere be? And that's what we're after. So we're going to do some approximations. Mathematicians like to do that, specifically mathematicians and engineers. So we're going to say that this balloon, when you inflate it to that volume, takes on a spherical shape. So do a little formative assessment. Maybe you want to write this down somewhere, working with your students. What's the formula for volume of a sphere? I promise not to take you through the integral. So we could say V sub s is equal to 4/3, and that comes from the integration of the surface area of a sphere multiplied by our favorite constant ever in a day that's coming up soon, pi. 4/3 pi, and then the radius, and this is a cubic function. Okay, so we need to solve for r. And you say, why do we need to solve for r? Well, it's really hard to measure r on a real live object, such as a balloon that is massive and full of helium whipping around in the breeze. So what we need to do is solve for r a very clever way so that we can ultimately find circumference of the balloon, because we could easily wrap a string around this balloon to measure its circumference. Then, by way of knowing if we have that correct r, we have that correct volume. So in this equation, I'm going to solve for r. And you can take your students through this. You might be familiar with it. Let's say I'll divide both sides by pi initially, because why not, right? And pi divided by pi is 1, so we have Vs over pi. I guess I should be saying V sub s is 4/3 r cubed. That's good news, right? Let's do another step here. How about, let's divide by the fraction 4/3. So when we divide by a fraction, we can actually multiply by its reciprocal. So I'm going to do this in a little bit more fancy of a step. So we say 3/4 times what we already have on that side of the balanced equation is equal to r cubed. One step remains. We need to get r by itself here. So it's a cubic function. We need to take the cube root of both sides. See, this card's coming in handy. I'm glad I used it. And we're left with 3 V sub s, again, volume of a sphere, multiplied by 4 pi. Cubic function is equal to r. All right, so that's an important formula, because most of the values, let's say on the left side of the equation, are constants. We know what 3 is, we know what 4 is, we know what pi is, and we also know what V sub s is. So if we plug those values in, we can easily determine an r value. And once we have that r, we can go plug into this equation for circumference. Help me out. Circumference is 2 pi r, right? So if we have r here, we can plug it into here for r, and then we can calculate the circumference. From there, we could get a string, wrap it around this balloon, and measure the circumference. That's how we'll know we have the correct volume in our balloon when inflated. So let's do it real quick. And by real quick, we need to do a little substitution of values and solve for units. So I'm going to take us through that right now. 3 multiplied by 78 and 37/100. Again, putting the units in there, this is in cubic feet. And we're going to divide that by what from our equation? 4 pi. Taking the cube root of all this, oh, good guess on that, is equal to r. So I again will pull up my TI-83 simulator, turn it on here. Remember, order of operations are important in this step. So 3 multiplied by 78 and 37/100. Got it. Divide that by 4 pi. Oh, where are you, pi button? Oh, I found it. 4 pi. Okay, and then we need to take the cube root of that. So let's put a step in here. Oops. I didn't forget, I just waited a little longer than I should. 18.709. And again, this is cubic feet. Now, notice because I'm not doing this all in one step, I'm losing some significant figures in here. Probably not the most appropriate thing to do, but I think we'll be okay. It's equal to R. Now, when I take the cube root of 18.709 cubic feet, I should be left with just feet, right? The cube root of cubic feet is feet. And now I'm going to take the cube root of that 18 value. 1 divided by 3. Oops. Close parenthesis. My radius of my balloon is approximately 2.65 feet. All right, this is a cool number. It's a cool number because when that balloon is inflated, to ensure that we have a volume of 78 and 37/100 cubic feet of helium in our balloon, I'm just going to write this again for good reason. I need a radius of a balloon that is 2.6 feet. And to go even a step further, because that's hard to measure in real life, let's say hard to measure accurately in real life in a balloon that is in space, I'm going to use a circumference equation. So help me out with this. I always seem to forget this one. Oh, I remember. Circumference equals 2 multiplied by pi multiplied by r after c, so 2 times pi, and I'm going to throw this value in, 2.65 feet. Calculate c. Go back to my TI. I'm going to take that number, multiply by second pi, multiply by 2. Come on. Oh, there we go. And drum roll, please. Circumference is approximately 16.68 feet. Okay, great, thank you. How about something I can use? Well, let's take that fractional part of that number and multiply by 12 inches. Yeah, right, your guess is around 7 inches, right? 8 and 1/6, so 16 feet, let's say 8 inches. All right, so when you're out there and you're filling it up and you've taken the circumference measurement, make sure that we're around 16 feet, 8 inches, and you will know that you'll have the volume. Where'd you go? There you are. The volume to get you to an ascent rate of that approximately 5 meters per second, and a burst altitude of around 73,000 feet. If you need anything, want to talk about this more, we could talk about maybe all you could do with this in the math class, please feel free to email me. My name is Jimmy Strand, but my email is a little bit more formal than I am. James_Strand@iu5.org. And remember, you are awesome. Take care.